Hey folks, Ms. Gosling here. In this video, you're going to learn about internal resistance. By the end of this video, you'll be able to define and calculate internal resistance. So let's go ahead and get started. So first of all, what is internal resistance? Internal resistance is the electrical resistance caused by the internal components of a cell. What I mean by that is that your batteries, such as this Duracell over here, aren't made of some magical resistance-free material. They're made of metal and chemicals and other things that all have their own internal resistance. They all will have some sort of physical quality that prevents electrons from flowing fully freely. Just like any material on Earth, except for, of course, our superconductors, which we're not going to get into in this class. So because of that, the voltage produced by a battery is different from the voltage output by the battery because some voltage is lost due to internal resistance, which we are going to represent using a lowercase r. So let's talk about the relationship between a few different parts of our of our circuit. So we can talk about the voltage, which is going to be our voltage output. So that is the amount of voltage that is put out from the battery. So the potential difference between positive and negative terminals. We're going to compare that to E, our EMF, our electromotive force, which is the voltage produced by the battery. And with that, we're going to talk about the internal resistance, and we're going to add a load resistor. So that is just some resistance that's added to this battery in a circuit. So first of all, we can look at our battery and that internal resistance of our battery as being in a series circuit with our resistor. So you can see here, we have our EMF, which is the voltage produced by the battery. And we have our internal resistance here. And then we have our load resistor. And so we can write this using Ohm's law as a super simple equation. And that is going to be, so we know, of course, that V is equal to IR in Ohm's law. And the voltage here is our EMF. And that is going to be equal to our current, I, times the total resistance of our circuit, which is our load resistor plus our internal resistance of our cell. So that's the first equation we can use. Our second equation is going to look at our voltage, which is, again, the voltage that is output by the battery. And that is going to be equal to our EMF minus our current times our internal resistance. That is, our output voltage is going to be equal to the voltage produced by the battery, our electromotive force, minus the voltage that is lost before our current even leaves the battery. Now, I can use these equations on their own, but there's one more thing that I can write. And that is, I can write that my EMF is equal to V plus IR. And of course, this is useful because I can't actually measure EMF in a lab. I can only measure my output voltage. So what this all tells us is the relationship between our EMF and our terminal PD, our terminal voltage. So again, these are going to be the two equations that you really use as you solve problems involving the internal resistance of a cell. So let's go ahead and solve an example problem. And what we're going to do is we're going to use our graph here to figure out the EMF and internal resistance of our cell, for which we get these voltage versus current readings. And this is the form that a lot of questions you'll get asked about this will take, because you guys are going to be doing a lab, and this is actually a lab that is required by the IB program, that where you get data using a graph like this one. So let's go ahead and give this a try. To start, I want to look at the equation V equals E minus IR, which I'm going to go ahead and rewrite as V equals negative IR plus E. So let's go ahead and compare that to our equation for a line, which is of course y equals mx plus b. Now, looking at our graph, we can pretty clearly see that our data is linear. And we know that on the x-axis of our graph, we have current, and on the y-axis, we have voltage. So we could write this as voltage is equal to m times I plus b. Now, I think this makes it pretty clear looking at the equation above this, our equation with voltage, what the relationship is between our graph, the different components on our graph, so our slope and our y-intercept, and our internal resistance and EMF. So looking at our top equation and our bottom equation, we can see that we have a voltage on both equations and that we have a current on both equations. We can also see that we have a thing that is multiplied by our current. So we've got negative R times our current, and we know that that is going to be equal to the slope of our line of best fit, because that's what's getting multiplied by I. It's the coefficient for I in our line of best fit equation, and it's the coefficient for I in our voltage equation. Similarly, we know that our EMF has to be equal to B, because again, that is the thing that is added to I in both equations. So what this means is if we find the slope of our line of best fit, that is going to be equal to our internal resistance. And if we find our y-intercept, that is going to be equal to the EMF of our cell. So let's go ahead and try that out. To do that, I'm going to start by trying to draw the line of best fit for my equation. And one thing that's important to know is that for a line of best fit, your line should go through the error bars at the very least of every point on this graph. You can see the line that I drew just barely does that. So we can easily read E, or well, it's actually called an epsilon, it's a fancy looking E, off our graph. It's going to be right here. And that looks like it's about 1.61 volts. So that is the EMF of our cell. Finding our internal resistance is going to be a little more challenging, but we know that negative R is equal to the slope of our graph. So we know that negative R is equal to the change in voltage over the change in current, which is something you guys are probably familiar with, having seen that before, right? V equals IR. So let's go ahead and pick out 2 points on our graph. And I want to pick points that are easy to read, but also kind of far away from each other. So for example, we can look at this point here, which is at, it looks like 100 milliamps. So 100 times 10 to the negative third. And going over to my y-axis, it's at 110, we'll call that. So we've got 110 times 10 to the negative third. And on our y-axis, we are at 1.55. And we can do the same with a second point on our graph. And I'm going to go ahead and find another nice looking point. So let's look at, I'm going to go ahead over to 500, go up to where that meets, and go all the way over. So our second point is going to be 500 times 10 to the negative third and 1.35. And we can go ahead and plug these points into our equation. So our change in voltage is going to be 1.35 minus 1.55 over our change in current, which is 500 times 10 to the negative third minus 110 times 10 to the negative third. Or if we want to rewrite this, 1.35 minus 1.55 over 0.5 minus 0.11. And that is, of course, equal to negative R. Now, I know I wrote delta V over delta E. That is the same as writing rise over run. I just wrote it this way because it's a little bit prettier. So when I stick all this in a calculator, I get that negative R is equal to negative 0.51. Or R, my internal resistance, is equal to 0.51 ohms. And there you have it, guys. We have figured out our EMF and our internal resistance just from a graph of voltage versus current. So that's pretty cool. So let's go ahead and talk takeaways. First of all, we know that all batteries have some amount of internal resistance. Second, we know that we can treat the internal resistance of a battery like a resistor that is in series with the other components of a circuit. And finally, we know that EMF is the total potential of the battery, while terminal voltage, or terminal PD, is the voltage difference between the two terminals of the battery. So internal resistance is the cause of the difference between EMF and PD. So there you have it, guys. You now know all about internal resistance, EMF, and voltage. So go ahead, try solving some problems on your own. Best of luck, and happy solving.